When Mendel conducted his famous genetics experiments with peas, one sample of offspring consisted of 428 green peas and 152 yellow peas. Okay. Use a zero point zero 0.01 significance level to test Mendel's claim that under the same circumstances, 25% of offspring peas will be yellow. Okay, so first of all, um, notice that it doesn't say anything about estimating a parameter, estimating the mean or the proportion or the standard deviation or the variance. It doesn't say that. Okay. Now, it's certainly related to that, but that's not what it's saying. Now it's saying test a claim, test the claim. So, two of the main things in this course are hypothesis testing, which is what we're doing here, testing, and confidence intervals for estimating a parameter. And we're going to see more of the hypothesis testing um, than the confidence intervals, but we're certainly seeing both. Okay, so we got to come up with the null hypothesis, HO, and the alternative hypothesis, H1. Um, use a zero point zero 0.01 significance level to test Mendel's claim that under the same circumstances, 25% of offspring peas will be yellow. So we're testing a claim about percents. So the parameter we're interested in is P. If it was saying test the claim about mean, then we would have had a mu there. Okay, so what claim are they saying? They're saying 25% of offspring peas are yellow. So they're saying, whoops, the proportion is 25%. Okay. And the other hypothesis needs to be the negation. So they can't overlap each other. They need to be mutually exclusive. So this one will be not equal to 25%. Now, one of these will always have the equal sign in it. Whichever one has the equal sign, that's HO. Okay, that is the HO. That is the null hypothesis. Okay, so that's our setup right there. So we know what our parameter is. We know we're doing a hypothesis test. And so now it's time to hit the calculator. We can do all this by hand, but let's not. So we're going to go stat over to tests, and we're going to go one proportion z-test because we're doing a test and it involves only a single proportion. Later on, we'll explore two proportions, but that day is not today. All right, so we'll go in there and so the first thing is it says, hey, what number is in your hypotheses? What do you think the proportion is? Or what are you testing it to be? Well, 25%. Okay. Usually the X and the N are pretty straightforward, but on this one it's slightly tricky, just slightly. So again, like we've seen before, X is the count of the number of successes. Well, in this case, success is yellow. Okay, because we're testing 25 to see if 25% are yellow. Okay, well, in our sample, 152 of them were yellow, so that's our successes. And then n is the sample size. Well, n is not 428 because 428 is only part of the sample. That's just the green in our sample. We also need the yellow from our sample. So 428 plus the 152, that'll be our total sample. And then for the next line, you look at the alternative hypothesis, H1. You look at the sign in there. We've got the not equal, so we'll take the default of not equal. And then we'll go down to calculate down there. Okay. So it gives us the results, and now we need to interpret them correctly. Um, so whenever possible, I'm just going to use the p-value method rather than the classical method for summarizing a hypothesis test. So our p-value looks like 0.502, a very large p-value. Okay, so now they tell us that alpha, the level of significance, is 0.01. Okay. So, because our p-value is greater than our alpha, then that means we're going to go with our conclusion is going to be HO rather than H1. And officially, what we're going to say is we fail to reject the null hypothesis. P equals 0.25 or 25%. Okay. So that is our official conclusion. So when you're doing these hypothesis tests, you can think of it this way. You can think the null hypothesis is on trial. Okay, and just like a defendant, you can either convict or fail to convict. Okay. And so that's what's going on there. So we don't have enough evidence to reject this claim right here. Doesn't mean that this claim is correct. We just don't have enough evidence based on what we see here to reject the null hypothesis. So that's the one we're going to go with. So the follow-up question was, what can we conclude about Mendel's claim? All right. So well, there's not sufficient evidence to warrant rejection of the claim that 25% of offspring peas are yellow. So we have said that already. And there is not sufficient evidence to conclude that Mendel's rate of 25% is wrong. Okay, so that basically answers the question. That's what I already said. Anyway, so that is what's going on. What's going on there. Now, because this was not equal in the H1, that makes this a two-tailed test. And so if this had been like a greater than, it would be right-tailed only. If it was a less than, it'd be left-tailed only. But I'm not worried about that in the video. Okay. Data set 21 and Appendix B in the back of the textbook lists earthquake depths, and the summary statistics are a sample of 600 earthquakes. X bar, I just wrote X bar because I'm in a hurry and I didn't know how to do X with a bar over it in Zoom. So sample mean is 5.82 kilometers in depth, and sample standard deviation is 4.93 kilometers. So fair amount of variation there. I mean, the standard deviation is almost as big as the mean. Use a 0.01 significance level to test the claim of a seismologist that these earthquakes are from a population with a mean greater than 5 kilometers. Okay, so here we go. So I see that it says test the claim. Okay, boom. So I know I'm doing hypothesis testing rather than confidence interval or something else. Okay. And let's see, we're testing a claim about the mean. Okay, so my parameter is going to be population mean, mu. And it says we want to do greater than 5. Okay, so I can do greater than 5 here, or I can do it down here. Because this statement does not have an equal sign, it needs to be H1. Okay, and then HO always has the equal sign. Okay, so we'll say equal to 5 right there. Okay. So we are testing a claim about mean. And so we're going to go to stat tests, and we can either do z-test or t-test. Well, just like with confidence intervals, we'll do z-test if we know the population standard deviation, which we don't, and that's normal. And we'll do t-test if we don't know the population standard deviation. So that's the direction we'll go is t-test. Okay, so the data was not given to us, so we're not going to put that in L1 and then use data, but we do know the stats. Okay, so mu, we're considering whether or not mu is 5, and the mean of the sample is 5.82, which is bigger than 5. So yeah, it makes sense. Hey, maybe based on the sample, we have enough evidence to suggest that the mean of these earthquakes is actually more than 5 kilometers deep. Sample standard deviation, we are told, is 4.93. And the sample size is 600. And we want to go greater than, because again, for this, you look at your H1. H1 has the greater than sign. We're going to go down to calculate, and we get all of our results. Now it's time to interpret. Okay, so we have a p-value of 2.6 times 10 to the negative 5. You can't forget the scientific notation stuff. If you do, it's going to give you a totally different answer. Alpha is equal to 0.01, the level of significance, and alpha this time is greater than our p-value. Therefore, we're going to go with H1. Okay, so officially we say, let me shorten that up a little. We say there is sufficient evidence. Well, actually, I should write this out more completely. At the 0.01 level of significance, or you can just say, just to make it easier, just say level of significance, there is sufficient evidence to reject the claim that, or well, to reject, yeah, the claim that the mean depth of earthquakes is 5 kilometers. Okay, so again, you're either rejecting the null hypothesis H sub O, or you are failing to reject it. In this case, we have enough evidence to reject it. Okay. And that is how we do it. Okay, here we are. Couples were recruited for a study of how many words people speak in a day. A random sample of 56 males resulted in a mean of 16,576 words and a standard deviation of 7,871 words. Okay, so use a 0.01 level of significance to test the claim that males have a standard deviation that is greater than the standard deviation of females, which is 7460. All right, now, so where are we at here? Okay, so first of all, I see test the claim, so I know I need an alternative hypothesis. I'm sorry, a null hypothesis and an alternative hypothesis. And of course, as always, the null hypothesis is on trial. Okay, so it says test the claim that males have a standard deviation. Ooh, so that's the parameter we're interested in. Okay. Okay, okay, so, well, HO is always equal. Standard deviation of 7460. Okay. So we get that. And our null hypothesis, oh golly, our alternative hypothesis, H1, is going to represent the other one, which is standard deviation is greater than. Okay, so greater than the 7460. All right, so now one thing that a lot of people have a tendency to do when they're first kind of doing these is when they get their results, they sort of interpret it as mean rather than standard deviation. And they say, oh, yeah, men use more words, or men use fewer words, or the same amount. It's like, no, 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 no. We're not talking about how many words. We're talking about the standard deviation of their words. In other words, how spread out are all the, are the number of words each man uses. This guy over here uses 8,000 a day. This guy over here uses 10,000. This guy uses 7,500. How spread out is that? Okay. Again, we're measuring standard deviation, the spread outness of the population. Okay, so we got that. So when you're doing a hypothesis test for standard deviation or variance, we are going to need to use the one of things in our programs, okay? And we're going to need, let's see, what was it again? It was a S2 test, okay? That makes sense. Okay, S2 has to do is S squared. So we're talking about variance or standard deviation. In this case, standard deviation, and we want to do the test associated with it. So that is what we're going to want to use in the programs. And as I've said before, I don't have the programs in this calculator. So we're going to go to here. All right, so when you go to S2 test, you'll put in all your data. Now, again, as we've seen on some of these others, it's asking for population variance. We're not testing for population variance. We're doing standard deviation, but that's okay. Just put in the population variance. So the standard deviation squared, which is what I've done. And then we're going to plug in the sample variance. So that's going to be our sample standard deviation squared. Okay. And then, of course, you put in the sample size, no big deal. And then it'll say, hey, do you, which sign do you want to use? And as always, you're going to look at H1 for that sign. So I picked the greater than sign because that's what's in H1. And then it says, hey, here are your results. Here are your test results, Mr. Smith. So we get a p-value of 0.26, pretty big p-value. And alpha is pretty much no matter what you have for alpha, alpha is going to be smaller. P-value is going to be bigger. So we're going to be going with HO. And so give me 1 second. And so what does that mean? Okay, so we might write something like, let's see if I can find a nice place to do this, or I won't overlap anything and you can read it. Okay. You might say at the 0.01 level of confidence, I'm sorry, level of significance. I did level of confidence last time. Oh, sorry about that. Level of significance. There is insufficient data evidence, I should say, evidence to reject whoops, that's not an H. O, that the I'm just going to do this. Standard deviation of the number of words that men use in a day, it was 1 day, yeah, in a day, is equal to 7460, the standard deviation of the number of words that women use in a day. Okay, so you want to write out your conclusion in a way that, most people can walk off the street and read it and say, okay, I got a pretty good idea of what you're talking about. Okay, and I'm fine with the abbreviations on tests and things. As long as it's something I'm going to know what it means. If it's just sort of out of nowhere, I'll be like, I don't know what you're talking about. So anyway, but that is how it goes. So now, is the standard deviation of the number of words that a man uses in a day equal to 7460? No, not likely at all. Even if it's close, it's probably like 7461 or 7459. Okay, but we don't have enough evidence at this point to conclude that HO is wrong. Okay, and that is going to do it.